Alright, so this is going to be my solutions to the third free response questions, or the third free response question of 2019 AP Chemistry. It says a student is given 50 milliliters of a solution of Na2CO3 of unknown concentration. To determine the concentration of the solution, the student mixes the solution with excess 1 molar calcium nitrate, causing a precipitate to form. The balanced equation for the reaction is shown below. And part A says to write the net ionic equation for the reaction that occurs when the solutions are mixed. So this whole solution, right? Sodium and nitrate are always soluble, meaning they won't form a solid. And in this case, this is just a normal precipitate reaction, and the net ionic in a precipitate reaction is the ions of the salt forming into the formed salt, the formed precipitate. So this is simply, well, that sodium isn't going to create a salt because it's always soluble. So CO3 -2 plus calcium +2 forming that precipitate. And you may want to put the state there just because it's not obvious, but you don't really have to put the aqueous state here because the charge is already implied it's aqueous. So that's part A. Part B says the diagram here below is incomplete. Draw on the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. So this is really a question that I'm really not sure to answer because, well, for one, according to the reaction, the Na2CO3 was a limiting reactant, right? So there's not going to be, per se, any Na2 or Na plus ions that are associated with the aqueous solution. All the Na plus ions are going to be associated with the nitrate solution. So there needs to be just as many sodiums as nitrate because these both have the same subscript of 1. And there's 4 in here, there's 2 in here, so I'd add in 2. Here, I'll draw that out better. I'm not going to draw 2, I'll just say ×2. So that needs to be in there. But what I'm unsure of is drawing in the calcium, because it says that the calcium is in excess, but it doesn't give you the amount of volume that was in excess. So you don't really know how much is in here. I remember putting in, I think, 1 calcium ion. But possibly I could be wrong because it asks you to represent the major ionic species, and it's not necessarily major because it's in excess. So I'm not really sure to answer that. I know this has to be here, but I'm not sure about the amount of calcium that needs to be, or calcium ions that need to be in the solution, if any at all. So I can't say anything about that answer. Part C says determine the number of moles of Na2CO3 in the original 50 ml solution. So this is simply a stoichiometry problem. So there's 0.93 grams of the precipitate, so it's simply 0.93 grams of the precipitate to this compound because it's simply the limiting reactant. So we'll go 0.93 grams of the precipitate, and it gives you the molar mass, which is 100.1. 100.1 grams, 1 mole. And this is the same because there's 1 mole of the precipitate per 1 mole of Na2CO3. Make that more obvious with the decimal. So 0.93 divided by 101. 0.93 divided by 100.1 is 9.29 times 10 to the negative 3 moles. And that's your answer for part C. We'll label that. Part D says the student realized that the precipitate was not completely dried and claims as a result the calculated concentration of Na2CO3 is too low. Do you agree with the student's claim? Well, the answer is no. His claim is not right. And the reason is because the precipitate not being completely dried would result in the mass of the precipitate being overestimated. And as you can see here, if you increase this term of the mass, you're also increasing the amount of moles calculated, which will therefore increase the volume, or which will therefore increase the calculated concentration. So the idea here is that if it's not completely dried, it wouldn't underestimate the true molarity, it would overestimate it. I'm not going to write that out, but that's the answer to it. And yeah, that's simply part D. Part E says, after the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be a ZERB? Justify your answer. So the answer is that it will conduct electricity. And the reason is all ionic compounds, when dissolved in water, will conduct electricity just because of their nature, their ability to conduct the movement of electrons. And essentially the solution here is a solution of many ions, sodium ions, nitrate ions, calcium ions. So because the solution is made of free ions and is physically the same as an ionic compound being dissolved in water, it will conduct electricity. The next part says, the student decides to determine the molarity of the same solution using a second method. When it's dissolved in water, CO3 negative 2 hydrolyzes to form HCO3 negative as shown by the following equation. Part F says the student wants to first determine the concentration of hydroxide in the solution, then use that result to calculate the initial concentration of CO3 negative 2. And FI says identify a laboratory method, not titration, that the student could use to determine the concentration of OH in the solution. So the answer here is, or at least what I put was spectrophotometry, and that's the idea of putting something in a cuvette and shining light through it and measuring the absorbance of light. Now, the main concern that I had here was that if you were able to perform this on solutions of many substances, because it makes sense that you'd be able to use that to find the concentration of a solution of a single substance. But we didn't do much spectrophotometry in my class, so I wasn't really sure about this, but I later found that each of these substances will have a different maximum absorbance wavelength, meaning maximum absorbance wavelength setting, or the wavelength setting on the machine that allows for the most absorbance. So if you simply find the maximum absorbance for hydroxide and use that, then the light will only be significantly absorbed by that hydroxide, which means that you can find the concentration of the hydroxide using A equals ABC, which is on your formula sheet. Absorbance equals path length times molar absorptivity times concentration. So the answer there would simply just be spectrophotometry. It doesn't ask you to justify. It doesn't ask you to set up a lab procedure. I actually remember setting up an entire lab procedure, and then I had to cross that all out because A, it didn't ask me to do that. B, the lab procedure was just straight up wrong. So I had to cross it all out. Simply the answer, spectrophotometry. There is a bit of a debate whether you could have wrote and use a pH meter. And I think that would be the only accurate way of representing a pH. Many people said litmus paper. The problem with litmus paper is it doesn't give you a quantitative value of the pH, right? It just lets you compare two solutions to see which one is more acidic or more basic. So you'd have to do something that could give you a numerical answer because you need a numerical concentration of the hydroxide. And yeah, that's your answer for part FI. I'm not sure if you could put pH meter because I'm not sure if that counts as a laboratory method. Spectrophotometry is definitely a lab method or in a lab procedure. So I'm almost positive you could have put that for FI. F double S says explain how the student could use the measured value in part FI to calculate the initial concentration of CO32 negative. Do not do any numerical calculations. So the way that I said this was simply use an ice chart and use your KV value. And I'll set up the ice chart. So CO3 2 negative plus H2O forms into HCO3 negative plus OH minus initial change equilibrium. It's a liquid, so there's nothing there. I called the initial value y. I called the change, well, the change is going to be negative x. So the equilibrium concentration is y minus x. And then this is going to be 0, 0 plus x, x, x. And here you could assume 5% since this Kb value is very small, so therefore y minus x is approximately equal to y, which is the initial concentration we're trying to find. So Kb is equal to x squared over, we'll put it approximately equal to x squared over y. You can solve for y, which is x squared over Kb, and x is simply the initial concentration of hydroxide, or the final concentration of hydroxide. And I think that's apt justification. You don't really need to justify it in English. But yeah, this is honestly fine. I'd honestly circle the answer just to be clear that that's what you're talking about. And yeah, that's your answer for part G. Part H says the student needs to make a CO3 negative, HCO3 negative buffer is the Na2CO3 solution suitable for making a buffer with a pH of 6. Explain why or why not. So the answer is no. And the reason why is during a buffer region, well, first we're going to be straightforward and call that G, but next we're going to be straightforward and calculate the pOH because this is important for the justification I'm about to make. So the pOH is going to equal 14 minus pH, which is 14 minus 6, which is equal to 8. And in a buffer solution, if you remember the formula for a buffer solution for the pOH, it's pOH equals pKb plus the log of the salt over the base. You may see this ratio written differently. I read it this way, it's just easier to remember that way. But during the buffer region, these concentrations are approximately equal to each other, right? And the log, or when these are equal to each other, the ratio between these is going to equal 1, and the log of 1 is 0. So during the buffer region, when it is a buffer, pOH should roughly equal pKb. pKb is equal to the negative log of Kb, which is the negative log of 2.1 times 10 to the negative 4. And while you don't really need to physically calculate this, I did, but it doesn't really matter for your justification because this value is going to be approximately equal to 4, or it's going to be no greater than 4. So we'll say the pKb is approximately equal to 4, and that means that the pOH is nowhere near pKb. So the solution is not a buffer, or suitable buffer. Suitable buffer. Yeah, it is a buffer, but it's not a suitable buffer with a pH of 6. Because that would mean that pOH would have to be about 8, and the pOH is about 4. Just based on the calculations we had before. So sorry if this is a little hand wavy. This is just the free response question that I was the least confident about. It's likely that I made the most mistakes on this one, but hopefully I give you a general idea of how this one should have been answered.